We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Myself, Divyang Patel, working as an assistant professor in Electronics and Communication Engineering Department at SHANKERSINH BAPU Institute of Technology, BAPU Gujarat Village Campus, Gandhinagar. Today I am going to conduct the lecture of the VLSI Technology and Design. So topic to be covered in this lecture is MOS inverters static characteristics. And then we will see the ideal inverters, VTC of ideal inverters, the nMOS inverters, VTC of nMOS inverters, resistive load inverters, their VTC, and the calculations of the critical voltage points. So first let's start with what is inverters. So inverter is a basic logic gates which converts the input into the complemented output. So let's see the symbols and the truth table of the basic inverters. So the symbol for the basic inverters, it has the single input and single output. Here the A is the input for the inverter and the B is the output. So B output is the complemented input. So here truth table shows the complemented output. Whenever the A input is 0, it converts into the 1, and whenever the A input is 1, it converts into the 0. Here as a MOS inverter circuit, we consider the logic 1 is as a high voltage and logic 0 can be represented by the low voltage. And the A and B both are working as a known voltage with respect to the ground voltage. So let's see the voltage transfer characteristics of this ideal inverter. Here the figure shows the voltage transfer characteristics of the ideal inverters. It means it is the two-dimensional graph between the V in versus V out. Here in the x-axis the input voltage is given and the y-axis the output voltage is given. Here the input voltage is given between the 0 to VDD. Here the VDD by 2 is working as a threshold voltage. So whenever the input is in between the 0 to the threshold voltage VDD by 2, it means the logic 0. At that time output is logic 1. And whenever the input voltage in between the threshold and the VDD, it means the logic 0, logic high. At that time the output is working as a logic 0 output voltage. So here threshold voltage is VDD by 2. So based on the threshold voltage, the input is converted into the output voltage. So this is the voltage transfer characteristics of the ideal inverter. Now let's see the nMOS inverter. So general circuit structure of the nMOS inverter. So here the input voltage of the inverter circuit is also the gate to source voltage of the nMOS transistor. That is the Vin equal to VGS. While the output voltage of the circuit is equal to the drain to source voltage, Vout equal to VDS. The source and the substrate terminal of the nMOS transistors is also called the driver transistor, are connected to the ground potential. So here the source and the substrate are connected. Here let's see, here this source and the substrate are connected with the ground, so that the VSB substrate and the source voltage is equal to 0. So here in generalized representation, the load device is represented as a 2-terminal circuit element. Here this load is the 2-terminal circuit element with the current IL and the terminal voltage VL. Here the current passing through this load is the IL load current, and the voltage across this load is the VL. Here the one terminal of the load device is connected to the drain of the N channel MOSFET. So here this load is connected to the drain of the N channel MOSFET here, while the other terminal is connected to the VDD. Other terminal of this load is connected to the power supply VDD. The output terminal of the inverter is connected to the input of the another MOS inverters. So consecutively, the next circuit seen by the output node can be represented as a lump capacitance Cout. Since the DC gate current of the MOS transistor is negligible for all practical purposes, there will be no current flow into or out of the input and output terminal of the inverter in DC steady states. So this is the function of the Cout capacitors. Now let's see the voltage transfer characteristics of these nMOS inverters. Here this is a gate, source, drain, substrate terminal. So now let's see the typical voltage transfer characteristics of this nMOS inverter. Here, by applying the KCL, Kirchhoff current law, to this simple circuit, we see that the load current is always equal to the nMOS drain current. In that case, here the load current IL is always equal to the drain current ID. So the voltage transfer characteristics describing the Vout as a function of Vin under the DC conditions. So here the Vout is as a function of Vin under the DC conditions. So here also here the general shape of the voltage transfer characteristics also somewhat similar to the ideal characteristics, but here due to the typical characteristics, it has some slope instead of drastically abrupt reduce in the low output voltage here. So here in that slope, we have the two critical points. That is at that critical points, the slope of these critical points is -1, which indicates the two critical voltage points, that is the VIL and VIH. And the point where the output is equal to the Vin, that is known as the threshold point VTH. Here the VIL, VIH, VOL and VOL are for the critical voltage points. Here the VOH means the maximum output voltage when the output level is logic 1. VOL minimum output voltage when the output level logic is 0. VIH is the maximum input voltage which can be interpreted as a logic 0, and the minimum input voltage which can be interpreted as logic 1. So this is the 4 critical point, as well as the 5th one is the threshold voltage VTH. So this is the typical voltage transfer characteristics for the nMOS inverters. So now let's see some noise immunity and noise margin. So sometimes in the inverter, when input is converted into the output by transferring the input from the output terminal, it added some unwanted signal due to the interconnections or due to some inductive or capacitive elements. So that is known as the noise. So to illustrate the effect of the noise, we consider these circuits. So in that, they assume that all the 3 inverters are identical, and that the input voltage of the first inverter equal to the VOH. It means the logic 1. By definition, the output voltage of the first inverter will be equal to VOL. So here the output is VOL here. This is corresponding to the logic 0 level. Now this output signal is being transmitted to the next inverter input via an interconnects, which could be metal or the polysilicon line connecting the two gates. Since on-chip interconnects are generally prone to the signal noise, the output signal of the first inverter will be perturbed during transmissions. Consecutively, the voltage level at the input of the second inverter will be either larger or the smaller than the VOL. If the input voltage of the second inverter is smaller than the VOL, this signal will be interpreted correctly as a logic 0 input by the second inverter. On the other hand, if the input voltage becomes larger than the VIL, that is the maximum allowable voltage VIL, as a result of noise, then it may not be interpreted correctly by the inverters. Thus, we conclude that the VIL is the maximum allowable voltage at the input, this one, input of the second inverter, which is low enough to ensure a logic 1 output. Now consider the signal transmissions from the output of the second inverter to the input of the third inverter. Assuming that the second inverter produces an output voltage of V0, VOH, this is. As in the previous case, this output signal will be perturbed because of the noise interference, and the voltage level at the input of the third inverter will be different from the VOH. If the input voltage at the third inverter is larger than the VOH signal, will be interpreted correctly as a logic 1 input by the third inverter. But if the voltage level drops below the VIH due to the noise, however, the input cannot be interpreted as logic 1. Consequently, the VIH is the minimum allowable voltage at the input of the third inverter, which is high enough to ensure a logic 0 output. So here, to logic 0 output, it must be required the minimum allowable voltage VIH. So this observation leads us to the definitions of the noise margin. So here, the noise tolerance for the digital circuit is called the noise margin, which is denoted by Nm. Noise immunity of the circuit increases with the noise margin. There are generally the two types of the noise margins are there. The noise margin for the low signal level, that is the NML, and the noise margin for the high signal level, that is the NMH. So here the NML equal to the VIL minus VOL, and the NMH noise margin at the high level is VOH minus VIH. This can be graphically represented as shown in the figure. So here the shaded area indicates the valid region of the input and output voltages, and the noise margin are shown as the amount of variations in the signal levels that can be allowed while the signal is transmitted from the output of one gate to the input of the next gate. The selection of the two critical voltage points VIL and VIH using the slope conditions, that is the dV out by dV in equal to -1. So here this figure shows the graphical representation of the noise margin. Here this is the NMH, here this one. This one is the noise margin at high, noise margin low, which is the difference between the VIL and VOL. Here the difference between the VOH and VIH. So now let's see the next point, that is the resistive load inverter. So here in the nMOS inverter, we consider the load as a normal two-terminal any device or any load components. So in that two-terminal component, we replace with resistor. So here the voltage across this resistor is VR and the current passing through this resistor is IR. So that's why it is known as the resistive load inverter. So here in the resistive load inverter also, the V is the voltage between the gate to source and the V output, that is the voltage taken from the drain terminal of the N-channel MOSFET, that is the driver MOSFET. So now this resistive load inverter also having the three operating modes, that is the cutoff, saturation and linear. Here, whenever the input voltage Vin is less than the threshold voltage, at that time the driver transistor is operating as a cutoff. Whenever the input voltage is in between the VTO and the Vout plus threshold, at that time the driver MOSFET is operated as a saturation mode. And the Vin is greater than equal to Vout plus VTO, at that time the MOSFET, driver MOSFET is operate in the linear mode. So now let's see the load current to the resistive load inverter. So here in this circuit, here the load current IR and the ID both are equal. So based on the IR equal to ID, we already derived the drain current equations for the N-channel MOSFET. So from the N-channel MOSFETs, we derive the equations for the load current for the cutoff mode, saturation mode and linear mode. So let's start with the cutoff mode. Here in the cutoff mode, any current can be passed from the load resistance and the drain terminal. So that's why in the cutoff mode, the IR equal to ID equal to I0. So the drain current ID equal to 0, so IR equal to also 0. Now in case of the saturation mode, the drain current equations in the saturation mode for the general N-channel MOSFET is shown in the figure. So this one. So here in this case we consider this IR equal to Kn by 2 Vin minus, here VGS equal to the Vin and the VT is equal to the VTO. So that the load current IR is equal to the Kn by 2 bracket Vin minus VTO square. And in the linear mode, the drain current equations is also shown in the figure. Here this one in the linear mode for the general N-channel MOSFET. So here we put our notations. It means the VGS equal to Vin, VT equal to VTO and VDS equal to Vout, which gives the load current IR, that is the Kn by 2 twice Vin minus VTO, Vout minus Vout square. So this is the current equations, load current equations in these three different modes: cutoff mode, saturation mode and linear mode. Here in the saturation mode, so we consider this lambda as a 0. So that's why this part 1 plus lambda VDS is 0, is 1. So that's why the IR equal to Kn by 2 V minus VTO square. So this is the load current for this resistive load inverters. Now the voltage transfer characteristics for the resistive load inverters. So this figure shows the three operating modes. Cutoff mode, during the cutoff mode, from the 0 to the up to voltage VIL. VIL is the critical voltage point where the slope dV out by dVin is equal to -1. So here the input is in between 0, it means the low input. At that time the output is converted into the high output VOH, that is equal to VDD at input is 0, and then slightly decrease the output voltage value, and whenever the slope is become dV out by dVin equal to -1, that is the critical voltage point VIL, then the output is drastically decreased. And when again the another critical point where the slope dV out by dVin is equal to -1, That point is known as the input high voltage VIH, and from the VIH the output goes to the VOL point, that is the output low voltage. Whenever the input is extremely high, that is the input is VOH. So here the three operating modes also shown in the figure: the cutoff mode, saturation modes, and the linear mode. So this is the VTC for the resistive load inverter circuits. Now let's calculate the critical voltage points for the resistive load inverter circuit. So that is the VOH, that is the output high voltage, output low voltage VOL, input low voltage VIL, input high voltage VIH. So let's start first output high voltage VOH. So here the output high voltage VOH. So to find out the VOH, we consider the Vout, that is the voltage between the drain and the source terminal here. So between the drain and source, this is the VDS. So here the Vout equations, Vout at this point, by considering the KCL, applying the KCL, the Vout equal to VDD, that is the power supply voltage, minus the voltage drop at the resistor. So that is the IRRL. So that is the voltage is multiplications of the current passing through the resistor and the value of this resistance. So Vout equal to VDD minus RL dot IR. But here the N-channel MOSFET is in the cutoff mode, so that IR equal to ID equal to 0, so that we put this value into the above equations, so which gives the Vout equal to the VDD. That is, the Vout is VOH, output high voltage, whenever it is in the cutoff mode. So that's why the value of the VOH is equal to the VDD. Now let's find the output voltage VOL. So to calculate the output voltage VOL, we assume that the input voltage is equal to the VOH. So here let's see in the figure. So here the input voltage Vin is VOH. So here the Vin is VOH. It means the high input voltage. Let's consider. So Vin equal to the VOH equal to the VDD. Since the Vin minus VTO is greater than Vout, so it operates into the linear region. Vin minus VTO is greater than Vout, so it operates into the linear region. So now let's apply the KCL at the load resistance node, at the output node. So that is the IR equal to VDD minus Vout upon RL. So using the KCL for the output node, it means the IR equal to the ID, we can write the following equations. So that is the IR is equal to the ID, so drain current. So we already derived the drain current for the linear mode. So we equate that VDD minus VOL upon IR is equal to the Kn by 2 twice VDD minus VTO VOL minus VOL square. Now we simplify this to find out the VOL. So we consider as a VOL square minus twice VDD minus VTO plus 1 by KNRL into VOL plus 2 by KNRL into VDD equal to 0. So this is in terms of the polynomial. So we find out the two roots for these equations. One is the valid one and second one is the invalid one. So here the valid one, it shows the equations VOL. So here this is the VOL equal to VDD minus VTO plus 1 by KNRL minus underscore under root VDD minus VTO plus 1 by KNRL whole square minus twice VDD by KNRL. So this is the equations for the output low voltage. So now next we'll find out the input low voltage VIL. So to find out the input low voltage, VIL is the smaller of the two input voltage values at the slope. By definition, VIL is the smaller of the two input voltages at which the slope of the VTC becomes -1 It means the dV out by dV in equal to -1. So apply the KCL at the output node. We have the VDD minus V out by RL, and here it is in the saturation mode. So we consider the drain current ID or the load current IR equal to the current in the saturation mode. So that is the Kn by 2 Vin minus Vto whole square. So here we derive these equations, above equations, these equations we derive it with respect to the Vin. So that by applying the derivation, we get the -1 by RL dV out by dV in equal to Kn Vin minus Vto. So here from this equations we apply the dV out by dV in equal to the -1. We already know. So to put the -1, we have the equations of the VIL, that is the VIL equal to Vto plus 1 by Kn RL. So now we apply this VIL into the above equations. We put this value VIL into the above equations and we get the final value of the VIL, V out when Vin equal to the VIL is this. That is the VDD minus KNRL by 2 in the bracket VTO plus 1 by KNRL minus VTO whole square. So here we put this above equation, this VIL equal to VTO plus 1 by KNRL. So we get the VDD V out equal to VDD minus 1 by twice KNRL. So now let's find out the input high voltage, that is the VIH. So by definitions, VIH is the larger of the two input voltages at which the slope of the VTC becomes -1. So here the KCL equations for the output node is VDD minus V out by RL is equal to the IR. IR is equal to the ID, and the drain current into the linear mode is this. That is the Kn by 2 twice V in minus Vto into V out minus V out square. So by applying the differentiation with respect to the V in, we get these equations. That is the -1 by RL dV out by dV in equal to Kn by 2 twice V in minus Vto dV out by dV in plus V2 twice V out minus twice V out into dV out by dV in. We put the value dV out by dV in as equal to the -1. We know that this is a critical point. So by putting this, we have the value -1 by RL. We put the dV out by dV in is equal to -1 equal to Kn by 2. Here the 2 is gone because by simplifying these above equations, by putting the dV out by dV in equal to -1. So we get this equation. We further simplify these equations to find out the VIH. So VIH equal to VTO plus twice V out minus 1 by Kn RL. So this is the input high voltage VIH value. So this all above topics is taken from the reference book CMOS Digital Integrated Circuit Analysis and Design by Sun Mokang, 3rd editions, Tata McGraw-Hill Publications. So thank you.